obviously, estimating speciation extinction rates is extremely fundamental to answering many questions in paleobiology, but speciation extinction rates also play an extremely important role in phylogenetics, and in particular in the estimation of speciation times. So, and throughout my talk, I just want to point out that when I use the term speciation, I mean it to refer to species origination. So, approaches that we have for estimating speciation extinction rates can be broadly categorized placed in two categories. Phylogenetic approaches based on phylogenetic data, and paleontological approaches that take as input stratigraphic range data. So, phylogenetic approaches use dated species phylogenies, and they use the information in the distribution of species divergence times. And this is because different combinations of speciation and extinction rates lead to different trees or different tree shapes, and so we can estimate these parameters from this data. The problem with these approaches is that they entirely ignore extinct diversity and don't do a good job of taking uncertainty into speciation times or topology into account. In contrast, paleontological approaches use use fossil occurrence data to construct stratigraphic ranges, and the input that they use are the distribution of first and last occurrences during different discrete geological intervals, and the proportion of first and last appearances during different intervals is used to inform the speciation and extinction rates. The problem with these approaches is that they typically ignore uncertainty in the timing of speciation extinction times, and they ignore the underlying phylogenetic process. And available approaches don't explicitly account for incomplete sampling in the estimation of the speciation extinction rates. So the fossilized birth-death process is a model that has four parameters: speciation, extinction, fossil sampling rate, and extant species sampling rate. And this is a process-generating model that results in samples of trees with extinct and extant taxa, and fossils sampled along internal branches of the tree, and samples in the present. And I've shaded this parameter here, rho, extant species sampling, because we often know a lot more about this parameter than the other three parameters, which are really much harder to estimate. And so this model has previously been used to estimate species divergence times using phylogenetic, when you have phylogenetic character data. But we're introducing a new version of the model, which can be applied to stratigraphic range data with or without character data. And I just want to mention that this is part of a broader, the maths and the model I'm presenting today is part of a broader project, and it belongs to a suite of models that for the first time enable stratigraphic range data to be incorporated into phylogenetic models. And these models also enable the process of morphological species evolution to be decoupled from the underlying branching process. And these models can be applied with or without character data. And today I'm specifically talking about the case where we have no character data, and instead we just have stratigraphic range data. And the information that this model takes as input are the first and last appearances, which, because not all possible combinations of these parameters, speciation, extinction, and sampling, can result in are not as equally likely to result in a given distribution of stratigraphic range data. So this information can be used to estimate these parameters from this information. So we implement the model in a Bayesian framework. We don't assume that the underlying topology is known, and we take care of that in uncertainty by integrating out all possible topological configurations of our stratigraphic data. We also treat speciation and extinction times as unknown parameters, and we can also co-estimate these using the model. So in total, we estimate speciation, extinction and sampling rates, along with speciation and extinction times. So I've implemented a version of this model in the phylogenetic program DPP-Div, and to assess the performance of the model, we performed an extensive suite of simulations using tools that are available in R. And today I want to mention three aspects of the outcome of these simulations. So how the results are impacted by variable sampling and preservation, how this model compares to popular alternative approaches, and how the results may be impacted by uncertainty in taxonomic assignment of stratigraphic ranges. So the sampling model, the underlying sampling model in the FPD model is a Poisson sampling process, and this essentially assumes that fossil samples are sampled at random across time and different branches. So constant during different geological intervals, which is obviously a gross simplification of the actual preservation and sampling processes. And so we tested our model using both the constant rate model and variable rate model. And in our variable rate model, we use a model of stratigraphic model of preservation. And in this model, each interval, the Poisson sampling rate varies. And so these are the results obtained when we estimate the parameters under constant rate model. And these are showing the speciation, extinction, and sampling estimates. And these are the Bayesian credible intervals. And the dashed line represents the true rates. And you can see that we do, under the models, under both low fossil sampling and high fossil sampling, we're able to recover these parameters. But you will notice that the credible intervals are really quite broad. And I should mention that the data sets we're using in these simulations have about between 1 and 200 species. Obviously, if you increase the number of species in your analysis, you can increase the precision with which you can recover these parameters. The model also fares quite well. Also fares well when the distribution of fossil species is non-uniform over time. But one thing to note is that under low sampling, you have these broad credible intervals. But at high sampling, you start to see a bias in the estimation of these rates. And the model does an extremely poor job of estimating the expected sampling rate. And so also looking at the ability of the model to recover the true age, and here we're focusing on the age of the origin of the tree. So the green line shows the estimate, and the black line shows the true distribution of origin times in our set of simulations. And you can see at low sampling, there's more of a mismatch between the estimates and the inferred ages than at high sampling. And we also see the mismatch persist when we have non-uniform fossil sampling. And we also compared the method to three fossil-based alternatives, the boundary crosser, three-timer, and gap filler approaches. And I should point out that these first three approaches don't take incomplete sampling into account in the estimation of the rates. They also assume that the data is uniform, but the data is filtered before the estimation of speciation and extinction rates. So these three methods partition the stratigraphic ranges data into different categories of taxa, and in the process throw out a lot of data that can cause biases as sampling is incomplete. So for example, these methods throw out all singleton taxa, so taxa that only appear in a single stratigraphic range. And so what we see with these approaches is that you get extremely broad and in some cases insufficient data to inform these parameters. But on the other hand, the fossilized birth-death model does quite a good job of recovering these parameters. And when sampling is high, these three approaches, the 3-timer gap filler and FBD model, do a good job of recovering the speciation rate, but we consistently see a difficulty and more uncertainty in our ability to estimate extinction. So this is showing the results under non-uniform or variable sampling over time, and we see tremendous bias when we have high non-uniform sampling in these other approaches, because here I haven't done any sample standardization, and so these methods can only work if you assume that sample standardization approaches have worked. And the final thing I wanted to mention is that we had a look at the impact of taxonomic uncertainty. And so morphospecies evolution occurs according to one of these three, has been proposed to occur to one of these three models, so budding, bifurcation, or anagenic speciation. In a budding speciation, each speciation event gives rise to one new species. And in the bifurcating model, each speciation event gives rise to 2 species and results in the extinction of the ancestor. And the impact of this, so we looked at this by assuming all speciation occurs through budding or all speciation occurs through bifurcation. And you see a huge expected discrepancy between the results. But the problem with this is that we don't know the underlying speciation model, and so the reality probably lies somewhere in between these two models of speciation. And so just to quickly conclude, we present a novel approach, which is, to my knowledge, the first model that can use stratigraphic range data to estimate speciation extinction rates along with times and account for incomplete sampling. And I just wanted to quickly emphasize that clearly one of the most important areas for further development is the handling of non-uniform sampling in these models, and also examining in more detail the impact of taxonomic uncertainty.